In this assignment I'll be looking at fatigue and recovery, which are associated with different durations and intensities of sporting activity. Fatigue is a mental and physical feeling most people gain during or after physical activity. It is defined as extreme tiredness resulting from mental or physical exertion or illness. Fatigue can occur due to the depletion of fuel stores within our body, accumulation of waste products, and thermoregulation. With fatigue comes certain side effects. An example of the side effects would be acidosis, which is the increase of acidity within our body, causing the pH levels to also drop. There are certain determinants of fatigue, such as intensity and duration, fuel, and waste products. There are also 3 different types of fatigue as shown on the screen: local, general, and chronic. Local fatigue is located within a localized muscle and occurs due to a repeated contraction of that muscle with the absence of recovery. General fatigue would occur after an activity has been carried out, resulting in an athlete feeling physically or psychologically weak. The final type of fatigue is chronic fatigue. This is when a player's immune system has been weakened due to the excessive overtraining and an inadequate recovery time. So here we're going on to maximal intensity and short duration activity fatigue. Here we have the 100-meter sprint as an example, which is performed at a high intensity, however a very short duration. Within this race, an athlete would use their ATP/PC system. This is because professional athletes such as Usain Bolt can run this in around 10 seconds. The only waste product produced is heat, and this isn't very harmful as it can be removed easily. The heat that is created is known as hypothermia, and this heat can decrease our performance a little due to the increase in core temperature. The energy systems ATP and PC are depleted at the end of the 100-meter sprint due to all their energy being put into the race, ensuring that they have performed to the best of their ability. ATP is depleted within the first 3 seconds of the race, and therefore the PC system is called upon to help create the energy needed to continue. This is shown within the graph that's on the screen now. At the end of the 100-meter sprint, an athlete would be feeling left exhausted, and this is the feeling of fatigue. From the graph we can see that ATP stores have completely depleted within just over 2 seconds, and the ATP/PC system depletes within 10 seconds. The recovery after the 100-meter sprint will be quick due to the fact that when we do exercise, there is a ratio which shows that for every 1 second of work that's done, it takes 10 to 12 seconds to recover. Recovery from high-intensity, short-duration activities is very quick. Throughout the recovery process, 3.4 litres of oxygen is needed to resynthesize the systems and get throughput back to the normal resting levels. We can see that from the graph that there's a depletion of PC, however, we can see that the PC store is also rebuilt during recovery. There are PC supplements which are used to prevent the PC depletion from occurring as quickly. This can be taken in powder form, and from this graph we can see the effect it has on the athlete. The black column shows how after taking the supplement the athlete's performance increased as the PC store doesn't decrease and deplete as quickly, and this is contrasted from the athletes that didn't take the supplements. Here we have an EPOC graph, which is excess post-exercise oxygen consumption. Within a high-intensity, short-duration sport, on the EPOC graph there is a very large oxygen deficit, which is temporary shortage of oxygen during the exercise. This is because it's an anaerobic activity, so oxygen isn't being used throughout the actual event. However, due to this, there is a much larger epoch. This means a lot of oxygen is consumed during recovery because of the oxygen debt in the event. This type of recovery is alactic fast recovery. Oxygen consumed during the event is used to during recovery is used to resaturate myoglobin and hemoglobin. This process only takes a few minutes. So next we have moderate intensity and moderate duration fatigue. Within this, I'll be looking at the 400-meter sprint as an example. On top of the AT/PC system for a 400-meter athlete, they will use their lactic acid system. The fuel used will be glycogen, and the two waste products are hydrogen and lactic acid. The acidity of the blood increases due to the hydrogen ions interfering with nerve impulses going to and from the muscles to enable contractions to occur. This inhibits the enzymes from working, making these muscles contractions weaker. The glycogen is stored from carbohydrates, and these are burnt more than fats during the 400-meter race, and this is because a person's RER. An RER is calculated by the amount of carbon dioxide which leaves the body divided by the oxygen intake per minute. In a 400-meter sprint, a person's RER is closer to 1, and therefore carbohydrates are going to be the primary source of fuel. From this OVLA graph, we can see the relationship of when the workload increases, so does the lactate levels. This results in fatigue within the muscles. In the filled-in triangle, we can acknowledge the point at which our lactate threshold occurs. Lactic acid builds in blood due to the LA system. OVLA shows a rapid increase in lactate within the blood. Effects of lactate accumulation is increased acidosis and decreased pH levels, which means that the enzymes are being prohibited, resulting in fatigue in performance levels. This will be an effect towards the end of the race and may cause the athlete to fatigue. Soda loading is a way to prevent the build of lactic acid from building at such fast rate. This is because it prevents the acidity, which means that the enzymes aren't stopped from reacting, and performance can carry out without us fatiguing quickly. This epoch graph isn't specific to the activity, however, if it was a large epoch and a large oxygen deficit would be shown due to it being an anaerobic activity. Lactic acid is converted as we need it, as we're using the lactic acid system. So 65% is converted to pyruvate. This enters the Krebs cycle and is made into energy. 5% is converted into glucose, which can be used as a fuel, and 20% is converted to glycogen. The final 10% is then converted into protein. During recovery from moderate intensity duration sports, both lactic acid and alactic acid recoveries are used. This is because the recovery is fairly quick and takes around 2 hours. However, sometimes DOMS can occur. This is delayed onset muscle soreness. It is caused by myofibril tears within the muscles, which is sore and can cause swelling too. Here we have submaximal intensity and low duration fatigue. For this, an example would be a triathlon or a marathon. And for this, our aerobic systems will be used, meaning oxygen is present. Energy which is used is glycogen and fat. As a result of this, the waste products are water and carbon dioxide, which don't affect the athlete in a particularly negative way. From this graph, we can see the depletion of glycogen throughout the exercise, as well as seeing the stores replenish during recovery. We see a rapid decrease in glycogen in the exercise stages. However, we see a gradual increase over the days of recovery. From the RER, again, we can tell that the primary fuel is fat, and fats will produce more energy within low intensity exercise, meaning a person can carry on for longer periods of time. It also means that we wouldn't be using up our glycogen stores. A technique which is used to increase our glycogen stores is carbo loading. And from this graph, we can see that within the first few days of carbo loading, we reduce our stores by increasing exercise and reducing the amount of carbohydrates we eat. This means that our body stores the glycogen from carbohydrates when we begin to carbo load and eat more carbohydrates. So on the graph, we can see that there's an increase in glycogen stores after carbo loading. Recovery from submax exercise is fairly quick, as we can see on the EPOC graph. It shows that the oxygen deficit is a lot smaller than maximal exercise, and this is due to the fact that we are working aerobically. And because of the oxygen deficit being smaller, the EPOC is also smaller, as there isn't as much oxygen needed to be paid back. We also see that steady state is reached. The recovery used for submax exercise is alactate slow recovery, which helps get rid of the prime waste product, which is carbon dioxide. However, also lactacid fast recovery is used to resaturate hemoglobin and myoglobin with the oxygen.